This is the next video in a series on electronic structure and periodic properties. We talked all about energy last time and how energy can be considered a wave or a particle. And in this series, we're going to talk about how matter can also be modeled as a wave or as a particle. So first of all, here in our structure, our outline for the course, we talked about the quantization of energy last time. So we want to check that off in our atoms section of the plan and move on towards the electron configuration section. So let's start out with wave-particle duality. We talked about this in terms of energy before, and now we're going to move on into the future and consider matter. So last time, we said light waves also have particle properties. They can be modeled very well as waves, but there were some features that couldn't be explained by considering light as a wave, so we had to consider light as a particle as well. We're going to call this now. So today, we're going to see if we can do the same thing for very small particles of matter, such as electrons. So matter, which we generally consider and model as particles, also has wave properties. So the most important contribution to this chapter of the story was in 1925 by a scientist named de Broglie. And he was the one who first proposed this completely outlandish idea. Scientists were already pushing their understanding of science when they said that light could be a wave and a particle at the same time. That was already a contradictory theory that took a long time to understand. But then de Broglie entered and suggested that matter could also behave as a particle and a wave. It was almost too much to understand. So de Broglie's PhD thesis was about wave-particle duality of matter. He proposed that microscopic particles, like electrons, very, very, very small particles, can be modeled as waves. And so what he said is that particles have some properties, some variables that relate to them. So if we're talking about particles, we can describe their mass and their velocity. And mass and velocity are related to a wave property. So mass, which is m, times velocity, which is v, is related to this property that's represented by the variable rho. And it looks kind of like a lowercase p. So there's velocity, mass, and this one is the Greek letter rho, which represents momentum, something we use in physics a lot. So mass and velocity are particle properties. Momentum is more of a wave property. So waves have momentum and wavelength. So to model matter as a wave, he related these particle properties and these wave properties together using this formula. Wavelength equals Planck's constant, h, over mass times velocity. Or if we substitute in this rho, wavelength equals Planck's constant over momentum. So we've got this guy, lots of variables here. All right, so we have h, we've seen that before. That's Planck's constant. And remember that was 6.626 times 10 to the negative 34th joules times seconds. This is rho, which is momentum. This is mass with a unit of kilograms. This is velocity. And note, this is an actual lowercase v for velocity, not the same as the cursive lowercase v for frequency. So velocity is in meters per second. And so momentum, which is mass times velocity, is kilograms times meters per second. And it's related to joules because joules is kilograms times meters squared per second squared. So the units should all work out. And then over here, we have the wavelength, specifically called the de Broglie wavelength, after the man who invented the formula. And the de Broglie wavelength is characteristic of a particle. So every electron would have the same de Broglie wavelength. It's a wavelength that's approximately the same size as the particle. And so you can see here that here's mass and velocity. Those are the particle properties. So this half is more of a particle representation, and rho, which is more of a wave property, this is more of a wave half. So trying to describe particles and waves with a wavelength. So let's do an example to see how this might be a useful formula to use to model a particle of matter as a wave. So in the example, here are two particles of matter. One of the particles is Superman, who weighs 100 kilograms, and the other particle is an electron, which weighs 9 times 10 to the negative 31st kilograms. And you may be wondering why we chose such a large object to represent a particle, and that is because in order to use this formula, the particles or the particle-like objects need to be moving at almost the speed of light. And the only large object that I know that moves almost the speed of light is Superman. So let's say that both Superman and an electron are able to travel at 1/5 the speed of light. Which of these is going to have the longer de Broglie wavelength? So we can use the same calculation for each of them and find out what size the wavelength will be, and then we can determine which one is the largest. So we'll do Superman first. The Superman is the biggest. So if we want to find the de Broglie wavelength, we'll use wavelength equals Planck's constant over mass times velocity. Let's see, what do we know? We know Planck's constant, it was given up here. So 6.626 times 10 to the negative 34th joules times seconds. Then we need the mass in kilograms, which is 100 kilograms for Superman. And then we need the speed, which is 1/5 the speed of light. So we'll multiply 1/5 times the speed of light, which we used in previous lectures, 2.998 times 10 to the 8th meters per second. And our unit should cancel out on the bottom with the units inside of the joule. And so the wavelength we can use to model Superman and his flight is 1.105 times 10 to the negative 43rd meters, which is a really, really small wavelength. But let's look at the wavelength of the electron first. Which should be more reasonably sized. All right, an electron, same formula. Much of this is going to be the same. Planck's constant is the same in the numerator. But we're going to have a significantly smaller mass is going to be the difference. So our mass for an electron is 9.109 times 10 to the negative 31st kilogram. And this is also moving at 1/5 the speed of light. There we are. So we can probably make an informed guess. If we have the same calculation, but a number in the denominator is significantly smaller, that means the answer is going to be significantly larger. So the wavelength for our electron is going to be 1.213 times 10 to the negative 11th meters. So the question wanted to know which one has the longer wavelength. So we've got an electron has a wavelength of 10 to the negative 11th meters, and Superman is 10 to the negative 43rd. So they're both very, very, very short, but this one is technically the longer one. And if we try and put into perspective how long of a wave this is, the electron is 10 to the negative 11th meters for its wavelength, and this is about the size of an X-ray. It's about the same wavelength as an X-ray. So that means that when we try and model an electron as a wave, we're actually pretty successful. It's about the same size as a wave that we're able to reproduce in a laboratory. So we can use X-rays to study electrons because they're about the same size. On the other hand, we have Superman, and the wavelength of Superman's flight is 10 to the negative 43rd meters, and that is super duper small. It's so small that we don't actually have any instrumentation that's able to detect waves with a wavelength that it's this small. We can only detect down to about 10 to the negative 14th meter sized waves. So it really isn't very helpful to model Superman as a wave because we can't actually use any waves to measure that flight of waves that small. You probably feel uncomfortable modeling Superman as a wave, and I think we all do, and that's fundamentally because it's not particularly helpful to model something that heavy as a wave. But for an electron, something that's really small, it can be helpful to model as a wave because we can generate waves of the same size to use to measure it. So one other related issue to the momentum and the position is how precisely we can measure these things. The more closely we zoom in on these tiny, tiny particles, and the more advanced our technology becomes, the more we realize that there is a limit to how well we can measure something. So let's talk about the Heisenberg Uncertainty Principle. So we have talked about the wave-particle duality of matter, how we can model certain types of very small matter as a wave. But because we're modeling it sometimes as a wave and sometimes as a particle, there is a limit on our precision. So this model limits how precisely we can measure the properties of microscopic particles, like the electron. So there is a definite limit in place to how precisely we can measure it. Let me show you how this works. We can model an electron as a particle, which is the way we've usually modeled it up until this point. And we can also now model it as a wave using de Broglie's equation for wavelength. And there are certain variables that we're interested in measuring for an electron. For example, we're really interested in finding out the position where is the electron? Where is it in space? And that's represented by x. We're also interested in figuring out, measuring the momentum of an electron. As we talked about on the previous page, we use rho to represent that, because momentum is related to speed, how fast it's moving. And for each of these models, it's easier to measure one variable or the other. So, for example, take the particle model. If you were to model an electron like a particle, it's very easy to determine the position of a particle. So you would be able to measure this, and your measurement would be highly precise. However, it's very difficult to measure the momentum of a moving particle. It's much easier to measure the position than the momentum. So the momentum measurement in the particle model would be not very precise. If we modeled an electron as a wave, the opposite would be true. It's difficult to measure the position of a wave because a wave kind of takes up space and it kind of doesn't. So it's difficult to tell when it crosses the finish line. However, it's much easier to measure the speed of a wave or the momentum than it is to measure the position. So the way this works, depending on which model we choose, we can measure one of these variables very precisely, but the more precisely we measure one variable, the less precisely we are able to measure the other. And that is a summary of what Heisenberg's uncertainty principle states. So in simplified language, Heisenberg's uncertainty principle says we cannot precisely measure both of these variables at the same time. We can measure the position precisely if we use the particle model, or we can measure the momentum precisely if we use a wave model, but we cannot in one single measurement precisely measure the position and the momentum. The way it works is the more precisely we know one of the variables, the less precisely we know the other one. And so for these two particular variables, we can define the limits to how precisely we can measure them using a formula. And in this formula, we use this triangle to represent our precision or our uncertainty for a particular variable. So when I put the triangle in front of x, it indicates the uncertainty in x, or the uncertainty in position. So in the formula, the uncertainty in position multiplied by the uncertainty in momentum, that product is always greater than or equal to Planck's constant over 4 pi. So the smallest value that this product can have is h over 4 pi. H over 4 pi is that fundamental limit to how precisely we can know something. And in the formula, we have Planck's constants, which we showed earlier. Pi is 3.14 and so on. X is our position. And rho is the momentum. So this is one of the special features of entering into the quantum realm, entering into the realm of things that are very, very, very small particles of matter that can be modeled as waves. is that there is only so far we can take our measurements. There's only so much precision that we can have. In the next video, we will talk about how to model an electron as a wave a little bit more in depth.